The fundamental theorem of calculus. Part 1. Okay, here we go. Fundamental theorem of calculus, part 1. If f is a continuous function from on the closed interval from a to b, then the function f of x equals the integral from a to x of f of t has a derivative at every point x in a to b, and the derivative of f of x is the derivative of the integral from a to x of f of t dt, which is f of x. I know there's a lot of f's in there. Remember, the capital F's are the antiderivatives. So if I have a function f of x that is the integral from a to x of the antiderivative of f, or sorry, the derivative of f. The integral is, you have your function f and the integral of the derivative of f. Okay, so these are the function, and this is a function and its antiderivative. This is a function and its derivative. Remember, they go back and forth. This ties into what we were doing on Monday. Okay. It says the derivative of an integral from a constant to x of a function is that function at x. Notice it's f of t dt, not f of x dx. It's f of t dt. That's an important thing because the variable in my integral is different than my variable of integration. The variable of my upper bound is different than the variable of integration I have, but the function remains the same. So what that's saying is the derivative of a function from a constant to x is that function at x. Okay. Now, it seems simple enough, but it is very hard, and have this down, very hard to underestimate the power of this equation. It says that every function is the derivative of some other function. Every function is a derivative of another function, namely the integral of that function. It says that every function has an antiderivative. It says that the process of integration and differentiation are inverses of each other. These are really important big concepts. Every function is the derivative of another function. Every function has an antiderivative. Every function has a derivative. Every function has an antiderivative. And they are inverse functions. Derivatives and integration are inverse functions of each other. That's a huge statement. It lets us do a lot of really important things. Now, I will say every function has a derivative. That's easy to find. You can find the derivative of any function, relatively speaking easy. But if you follow the rules, you can take the derivative of any function. The antiderivative does exist. However, finding the antiderivative of every function, oh, that's a whole different story altogether. And it is really, 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 really hard to do the antiderivatives of some functions. It's actually not difficult. I can write one up like that would be almost impossible to figure out the antiderivative by hand. You'd have to be a whole lot smarter than I am to be able to do it. And probably it's impossible to find by hand. But there are other ways of doing integrals without antiderivatives. So there are other ways of dealing with those problems. But they do exist. Every function has a derivative. Every function has an antiderivative. And the two in integration and differentiation are inverse functions of each other. That concept is probably the biggest part, or one of the biggest parts of the fundamental theorem of calculus. It is called the fundamental theorem of calculus for a reason. It is fundamental. It is important. And this is part 1. And this part, saying that integration and differentiation are inverses of each other, is a huge statement to make. It's a huge statement to make. Now, the actual work that's involved with part one is a lot simpler than it seems simple compared to the power of the concept. Okay, but this is an extremely powerful statement saying that we can do this. And the work itself isn't that difficult. Okay. So it's basically, for part one, it's taking the derivatives of an integral. And the derivative of an integral from some constant value to x, any constant to x, where the constant is the lower bound and x is the upper bound. It's really easy to do it. Replace t with x. That's it. There's a nice proof of this, but the proof of this actually requires a fundamental theorem of calculus part 2. And I'm not going to go yeah. But yeah, that's what you do. You just plug in the upper bound. Plug in x. You don't change the equation. You're not going to take the derivative of the equation. You don't take the antiderivative of the equation. You just do this because you're taking the derivative of the integral. And remember, the integral, you're taking the derivative of the you're taking the derivative of the antiderivative of a function. That's kind of what you're doing here. Because remember, if you go back to the rule, this is the antiderivative of that. When you take the derivative of the antiderivative, what do you get? You get your original function back. And that's what we're doing here. The integral from a to x is the antiderivative of f of x. So if I'm taking the derivative of both sides, I'm taking the derivative of the antiderivative, which would be what? The original function. So it kind of makes sense when you look at it like that. Because if I'm taking the derivative of both sides, if I take the derivative of the antiderivative, I get the derivative. I get the original function I started with. That's what we're doing here. Okay. Now, it gets a little complicated. That's the easy one. You just plug it in. This one, same idea. What's the derivative of from x to pi of 1 over 1 plus t squared dt? Well, my rule, my theorem, the fundamental theorem of calculus says I go from a constant to some function x. My lower bound is a constant, my upper bound is my function. I don't have that here. My lower bound is my variable, my upper bound is my constant. But we have rules of integration that let us flip them, right? So this is the derivative of negative integral from pi to x of 1 over 1 plus t squared dt. Because we have a rule that lets us flip our bounds. So if I need the constant as my lower bound, all I do is I flip it and I make the constant my lower bound and make it a negative integral. Okay. So the derivative of this, just make it negative. That's it. Ooh, it's so hard. Yeah, it's a simple rule, but like I said, there's a lot of strength and power behind being able to do that. Okay. Okay. Same idea. Y is equal to the integral from 0 to x squared of sine of t dt. Find dy dx. Well, I've got a little bit of thing going on here. So I want to do this. I want to find dy dx. Well, that's the derivative That's what I'm doing. Take the derivative of both sides. So, sorry, it's x squared. So dy dx equals sine of x squared. However, that is not just x on the top. Previously, when we changed our derivatives to not being just of x, but of a function, we had to apply the chain rule. We need to apply the chain rule here as well. If your upper bound is not just x, but some function of x, it's the same idea as a chain rule. I plug in that function of x, and then I have to multiply it times the derivative of that function of x. In this case, 2x. But to make it look pretty, as we should, you should bring the 2x in front. Just to make it look pretty. Just making these look pretty important. Okay, now this is about as bad as it gets. I want to do the same thing. Got a problem though. What am I supposed to have as my lower bound? Constant. I don't have a constant as my lower bound, do I? I have a function as my lower bound. And I have a function as my upper bound. The rule says that I have to have a constant as my lower bound. Well, I can make it happen by using our rules of integration. So y equals the integral from 2x to some constant of 1 plus 2e, 2 plus e to the t, e to the dtt, plus some constant a to x squared of 1 over 2 plus e to the t dt. We have a rule that says we can do that. Remember? The integral from a to b and plus the integral from b to c is the integral from a to c. Same thing. Only instead of having 1, we split it up. A is some constant that's between 2x and x. I don't know what it is. I don't care. It's just a constant. It will become irrelevant what that particular numerical value is at some point, so I don't really care. I'm just going to put some constant down. I don't want to put 0 because I don't know. 0 is technically between 2x and x squared, but I know there's got to be something between them. Unless x is 0, there's something between 2x and x squared. And if x is 0, it's irrelevant. Okay? So I can split it. Now, I still have an issue. My first one, what do I need to do to this? I need to flip it. Now flip it, change the sign.
I thought like the A's have to like line up like diagonally because like to go from like point A to point B and then from like point B to point C, you can't go from like point B to C. I thought like
they do here.
And you just be since they do.
Once through here, I can do what I want. Yeah, I can do what I want at that point. Yeah. And now I can go ahead and take my derivative. dy dx is equal to the derivative of my first integral, which is negative 1 over 2 plus e to the 2x times 2. Plug in 2x for t and then times the derivative of 2x. Plus 1 over 2 plus e to the x squared times 2x. Plug in the upper bound times the derivative of the upper bound. And then if I really want to make it look a little prettier, 2x, 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Just to kind of make it look a little prettier. Nice cake. Not real hard. And I think that's it. Yep. Once again, this is where it really gets important is this part here. Okay? Every function has an antiderivative, every function has a derivative, and the process of integration and the process of differentiation are inverses of each other. That's huge. Okay, that's huge, being able to say that I have two functions that are an inverse, because inverses are how you solve everything. When you had x plus 2 equals 3, how'd you solve it? You did the inverse of adding 2, which is subtracting 3 from both sides. Inverse functions is how you solve everything. Being able to have an inverse makes a big deal. Okay, that's a really big deal. The mechanics of today's lesson is taking the integral. That's not that hard. But the idea behind this fundamental theorem, that's a big deal. Okay.